Okay, we're going to start with what is calculus? Calculus is the study of limits. That's what this section is about. And within limits, we have two subcategories of limits. So rate of change and Riemann sums. And the rate of change is really the derivative, and we denote that with a little d in front of whatever we're doing. And Riemann sums is the integral, and we use a kind of a stretched out s for sum. Like I said, in this section we're only going to be dealing with limits. And if you want to complain to someone about calculus, you can complain to Leibniz and Newton. Unfortunately, they both passed away in the 1700s, so good luck in trying to file your complaint. Right, they pretty much discovered calculus about the same time, so they both arguably have credit for that. All right, in this section, we're going to be introduced to limits, and you will understand the concept of limits, be able to estimate limits, use properties of limits and direct substitution to evaluate limits, and determine the continuity of limits. First, when you see the term limits, I want you to start thinking trying to get to. It doesn't matter if it can actually get there, but it's just trying to get there. Start off with a little story. This is Little Red Riding Hood, and she's met up with a character, and this character asks her, "My little hooded friend, where are you going to?" She replies, "I'm on my way to my Nana's house to bring her some soup." So we have Nana's house. All right. So she's going to Nana's house. That's where she's trying to get to. But along comes a spaceship and beams Nana's house away to a totally different place. Now, if we revisit this little story, we can say, "My little hooded friend, where are you going to?" "I'm on my way to Nana's house to bring her some soup," because she's still trying to get to Nana's house, even though her Nana's house has been beamed away, but she has no clue that has happened. So that's basically the foundation of limits. Is in calculus we're able to calculate something even when we can't. We can try and get close to it, or wherever it's trying to get to. Pretty much is a good way of getting to the answer that we could not have normally done with regular mathematics. But let's bring this back into the math world. Here we have some kind of function f of x. And on the horizontal axis we have x. And the vertical axis we have y, or in other words we have f of x. And if we say the function of f of x is given here, and we want to find the limit as x tries to get to 5, what does the function trying to get to? Well, on the horizontal axis, if we let x try to get to 5, the function is trying to get to 3. As we're sliding along this path horizontally this way, we're going to be forced to go up with my graph until we come to this point right here, 3. 5, 3 would be that point. Okay, this is a pretty simple problem here. We don't even have to know what the function is. And in this case, the function is continuous, meaning that I can draw it without lifting my pencil. That's what continuous means, continuity. Okay? Now here's another function. In algebra, we could write this equation as 1/2 x plus 1, because that's the y-intercept is 1 and the slope is 1/2. Now, if we take this function and we ask, as x tries to get to 4, what is f of x trying to get to? Well, as x tries to get to 4, f of x is trying to get to 3. Okay, so we're trying to get to this point right here because we're going this way. Actually, in reality, in calculus, we have to approach it from usually from both directions. from the negative direction and from the positive side also. But right now we're just going to consider going from the left side. All right, so that's equal to 3. Now there's a different way. Whenever you see this, you should first try a direct substitution. That means you're going to put this 4, the limit for x goes to 4. So we're going to put the 4 in here. 4 times a half. Half of 4 is 2. 2 plus 1 is 3. So that's how we get this 3 here. Did that make sense? All right. So let's try a different one. What about for the same function, let the limit go to 6 for x. X is trying to get to 6. Where is the function trying to go to? Well, if we let x go to 6, looks like the function's trying to get to 4. Or if we're going to do a direct substitution, we can put the 6, substitute the 6 in for x. We'll get 1/2 of 6 is 3. 3 plus 1 is 4. And this is just the notation for that fact that we put in a 6 for f. All right, let's make this a little bit more complicated here. Before we do that, let's talk about continuity. The continuity of this function is continuous because I can draw that without lifting my pencil. Okay, let's make this problem a little bit more complicated here. Let's say that we pulled off a point and we put it somewhere else. That's what this piecewise function means. For the first piece, for everywhere where x is not equal to 4, I get to use this function. Where x is equal to 4, I have to use the 1. That means I've taken the 4 out of this domain and moved it somewhere else where I put the y down here. Okay, I've just moved the domain I moved the 4 out of this domain and put it down here, and I gave it a different value. That means, like the spaceship, I pulled it off of my graph and moved it somewhere else. Okay, so let's talk about what f of 4 is. F of 4, if x is 4, then I have to go, which formula do I use? I have to use this one because x is 4. I use this one when x is not 4. So when x is 4, that means f of x is equal to 1. Okay, that means everywhere this is equal to 1. Now, we're talking about everywhere but 4. As x tries to get to 4, what is that value? As x approaches 4 from the left, the function approaches 3. As x approaches 4 from the right, x also approaches 3. This is called the two-sided limit. That means we're trying to get to 4 from both sides, and we get to a value of 3. Okay, so the limit of x goes to 4 is the function goes to 3. Let's step this up just a little bit. I keep forgetting to mention the continuity. Is this continuous? Is this graph continuous? No, it's not, because I have to lift up my pencil in order to finish drawing this graph. There's nothing here, so I've lifted up my pencil, started up again, and finished the graph, and then put a dot down here. So it's not removable. I mean, it's not continuous, but it's removable because I've removed a point off the graph and moved it somewhere else. Now let's make this a little bit more interesting. Now you notice this looks like the same problem, except I put a little plus sign up here. That means that I want x to go to 4 from the large side, from the positive side, or from the larger end, all the bigger numbers. So as I approach 4 from the right side, this little plus sign means approach it from the right. What do we get to? Well, f of x is equal to 3. This is a one-sided limit. This little thing right here means it's a one-sided limit. We could also approach it from the left, another one-sided limit. From the left, the minus end, or the smaller end, we also get 3 because they're both going to the same place. All right. If we change it up like this, now we have all the numbers for x. The domain of x is smaller than 4, everything to the left on the horizontal line, and everything to the right domain, right, for x, we're going to use the second equation here. Now if I said we're going to approach it from the left, this function is going to go to 3. Okay. If we approach the limit as x goes to 4 from the right, Now f of x is going towards the 1. Okay? Or you can say I want to do a direct substitution here. 4 from the positive side, I'm going to put 4 here, and I get 8 minus 7 is 1. From the smaller side, I can put the 4 in here. 4 times a half is 2. 2 plus 1 is 3. Okay? So what is this graph continuous? No, it's not continuous. And this is not a removable continuity, so it's a non-removable continuity. This is actually, we're splitting the graph up into two pieces. We didn't just remove a point. When we remove a point, we call that a removable discontinuity. This is a whole different thing. This is a non-removable. So there's three choices: continuous, removable discontinuous, and a non-removable discontinuous. It's either going to be able to be drawn with your pencil without lifting up your pencil, with lifting up your pencil where it's removable, and with lifting up your pencil where it's not removable. Let's make this a little bit more interesting here. Let's make this a two-sided limit as x goes to 4. Two-sided limit. What would be the limit as x goes to 4 for this function? Think about it for a second. Give me an answer. All right. If I approach it from the left, I go to 3. Approach it from the right, I approach 1. So that means I can't make up my mind. Therefore, if you have seen Mean Girls, you'll know that if you approach two different values, the limit does not exist. Okay? Because it can't make up its mind, the limit does not exist. Okay, there's some other ways where the limit cannot exist. There are three different ways. One, where they're approaching two different values from the left and the right. And another way is if we took this graph, if we graph this, it should look like this, where if we're trying to get to 0 from the left and the right, we're going to go to infinity. And whenever x approaches infinity, either from the right or left, or from both sides, or even just one side, the limit does not exist. The limit cannot approach infinity. Okay? It must approach a real number. So the limit does not exist. The third way that your limit will not exist, if you want to talk about the discontinuity, this is not continuous because it's non-removable. It's going to infinity, and at some point these two are not going to be touching ever. Okay, even as you go higher and higher up, they'll never touch because the y-axis is at asymptote. All right, this is the third kind of discontinuity. Is usually when you have a trig function with x in the denominator and you're trying to get to 0, you're going to get this weird thing going on where the graph is going to swerve in and try to get towards 0, but as closer it gets to 0, can't make up its mind. It's going to go up, down, up, down, up, down, up, down, up, down, up, down, up, down. It's called an oscillating function. It bounces off between 1 and -1. Really cannot make up its mind. No matter which side you approach it from. Even if you approach it from the right, it's going to start swerving, and then it's going to go back and forth, up and down, up and down. It can't make up its mind, so we call this an oscillating function. As x approaches 0 from the left or the right, the function oscillates between -1 and +1. Because the function oscillates between 1 and -1, the limit does not exist. So there are your three ways that you're going to encounter in this class where the limit does not exist. All right. So is this continuous? Well, this function, it actually is continuous. It just fluctuates in the middle many, many times, an infinite number of times in the middle, but then it's continuous on the other side. So this function is continuous. Estimating a limit numerically. Okay, so we would normally just take this and do a direct substitution as x approaches 2. So we let x equal to 2. 2 times 3 is 6, minus 2 is 4. That would be my limit. But in case you plug it in and you get something weird like 0 over 0, that's called the indeterminate form. And then we're going to take this and we're going to make a table. We're going to take the x, put that in the middle, and we're going to sneak up on it from both sides. When we sneak up on it, we have to use really small numbers, okay? Like 0.001. We're going to get really, really close, but we're not going to touch it, all right? And then we're just going to get farther and farther away. And then we go closer and closer. From the other direction, we're going to sneak up on it from the smaller side and from the bigger side. And if you're not good with decimals, you know that this is 1,000ths, this is 10,000ths, and this is 100,000ths. This number is 100 times bigger than this number, okay? And this is 10 times bigger than that number, and so on. So this is 1 minus this number, 0.999, and this 0.990. This is 1 minus this number here, and this is 1 minus 0.100, and it'll give you 0.900. Okay, we're going to use our calculator to finish this table. Once we get our calculator to finish our table in table mode, we're going to get these numbers in here. So looking at this pattern, you can see 3.7, 3.97, 3.99 is trying to get to a number. 4.3, 4.03, 4.003 is trying to get to 4 in here, right? That's what we got up here. So therefore, as x approaches 2, the function approaches 4. Okay, in this problem, we're going to try to estimate the limit. All right. So numerically, we could try to plug in the 0. If we plug in the 0, we get 0 over 0 plus 1. Square root is 1 minus 1 is 0. So this is the indeterminate form that I kind of mentioned in the last problem. Indeterminate form means undetermined. I don't know yet. That's what this means. Yeah, there is a value, but I just don't know yet. So I make a table, put the 0 in the middle, and sneak up on it on both sides. Okay, you can use any small numbers you want as long as you get closer and closer this way and closer in this way. In other words, it gets farther and farther away as you go away from the number that you want. You put that in your calculator, and you can see this is sliding up to a certain number from both sides. So now we know that it's trying to slide up to 2, right? It's trying to get to 2 from the left and right. So the limit for this function is as x approaches 0, the function approaches 2. Is this continuous? No, because we moved the point there, so it's a removable discontinuity. All right. Okay, so this is your Google form. Here are your questions. Let's see. Number 1, name the continuity for the function. Is this function continuous, removable discontinuity, or non-removable discontinuity? Number 2, what is this? Number 3, what is this? Number 4, estimate the limit as x goes to 5 for this function. Estimate the limit as x goes to 3 plus from the positive. Okay, estimate the limit as x goes to 3 from the negative. And estimate the limit as x approaches 3. Number 8, evaluate the limit. Number 9, evaluate this limit. And last problem, evaluate this limit. Okay, thank you very much.